See, in the last lecture, so we saw this beautiful theory called as Hamilton-Jacobi theory. So, remember in the last week we had talked about the canonical transformation to such a coordinate frame that in the new coordinate frame all the canonical variables will be constants of motion, and we gave some examples, but then Hamilton-Jacobi theory gives us the procedure to find such a transformation. Okay. I will again recap this because it is very important. We will first talk about a system with 2n degrees of freedom and its Hamiltonian is described by H. Okay. Now, what we want to do is find that generator which makes this possible, makes the canonical variables constants of motion in the new coordinate system. Now, for S we know that S must give you, it must be of course function of old q, new momenta and time t, but then for the purpose of finding this function we will immediately begin with S which is function of q and t, and then what we are expecting is that del S by del q must be equal to old p, del S over partial derivative of S with respect to q, small q must be equal to old momentum variable. Okay. So, what we have here is a Hamilton-Jacobi equation constructed out of this. So, for the new Hamiltonian to be 0, del S over del t plus the Hamiltonian, where now p is expressed in terms of partial of S with respect to q, and this must be equal to 0. Okay. Now, what is this? This is a single differential equation for S which is function of n plus 1 variables, and we of course argued that how many constants of variable are there. There will be one constant of variable which will be just additive in nature, we are going to drop that one. Okay. So, finally, we get this complete solution S which is function of n q variables and t, and when you do the integration, of course, we are going to get n constants of motion, actually n plus 1, but one of those is irrelevant. See, the whole point of this procedure crucially depends on finding this complete solution, that means finding expression for S which is in terms of q and the constants of integration which are arbitrary in nature. Okay. So, once you have this, now what we are going to do is now we construct our generator by simply taking this expression, replace those alphas by capital P which are supposed to be new momenta, and once you do that you get this generator of canonical transformation which is, and the claim that we made is that this is the one, this is the generator that we want. Okay. So, the transformation equations now can be written as small p I must be equal to partial of S with respect to partial of S with respect to q I, and capital Q I must be equal to partial derivative of S with respect to capital P I. Okay. So, once we do this, I get, remember S is in terms of now q and p, I of course can invert these equations. So, we will get these two equations where old momenta, new variables are expressed in terms of old coordinates and new momenta. Now, what I am going to do is invert this and finally write the correct transformation equations which we want, which is new momenta and new coordinates in terms of old canonical variables. Okay. Now, see what happens. The Hamiltonian now is 0, this we looked at in the last class. Once the Hamiltonian is 0, I know that all the momenta and coordinates, they are constants of motion. Okay. So, basically your each p I, capital P I, which is function of q, p and t, must be constant, and what must be the value of that constant? Since we already know the transformation, if I plug in the initial point, that is that t is equal to 0, I already know q 0 and p 0, I know 2 n constants there. So, once I put those there, I get the initial value of p, and this is constant of motion. So, this is value which will remain for all values of time t, okay? And we will call this as alpha I. Same thing for the momentum, okay? The value of the momentum, that is value of the coordinate q I, capital Q I at t is equal to t 0 is beta I, and as the time evolves, the system moves on a trajectory, but the trajectory is just a point, because all the 2 n variables are now constants of motion. Okay. So, this is the typical program, and then how do I actually solve the, remember I finally want my answer in the first coordinate system, the old coordinate system, and that you can do by, see. So, I have this equation, this is the expression in q, p and t is equal to alpha I, there are n of these expressions, and there is this expression, again n of these expressions or equations equal to beta I. Invert this, once you invert this, you get old q I and old p I, all the canonical variables in terms of alpha I and beta I, which are just constant numbers, okay, and at any time t there, okay, at any time t. Now, we can of course do slightly better than what we have done here, if we already know that the Hamiltonian is independent of time, then Hamiltonian itself is one of the conserved quantities. Okay. So, let me look at that one now. If the Hamiltonian is independent of time, then what I am going to do is, to solve the Hamilton-Jacobi equation, I will assume that the solution for the Hamilton-Jacobi equation, that is capital S function, the action function, which is function of q and t, I will write it as two separate functions, one which is only function of q, that is called w, and the other one which is only function of t. Okay. And this is a way of separating the variables, or this method is called as a separation of variables, which I will again reintroduce later in the class. But now, once I do this, clearly if I take a partial derivative of s with respect to t, that is just del f by del t, because w is independent of t, and partial derivative of s with respect to q I will be partial of w with respect to q I, because f is independent of q. Okay. Fine. Now, let us put this back into the Hamilton-Jacobi equation. Once I put this back into the Hamilton-Jacobi equation, now del f by del t will be equal to minus of the Hamiltonian. And now you look at the two sides of this equation. One side, which is df by dt, which is completely function of t, and there is no q in it, and on the other side, on the right hand side, I have Hamiltonian, which involves only q and there is no t in it. So, this must be true for every q and every t. What does that mean? Both these sides must be independently equal to a constant, and let me mark that constant as gamma. Okay. Now, one of the solutions is straightforward, because the time equation looks very easy. That will give you f is equal to minus gamma t, that is a straightforward solution. And the second one, of course, is the differential equation in w with how many coordinates? That is just n. Okay. So, we will be finding w as a function of q, and because there are n variables, there will be n constants of integration. The same comment that we made for capital S function, or the Hamilton's principal function, will apply here also. Look at this differential equation. In this differential equation, w does not appear, only the partial derivative of w appears. So, w, if the w is a solution of this Hamilton-Jacobi equation, w plus some constant is also. So, one of these constants of course must be the additive constant, but anyway I will leave it here, because I want to use this gamma also. Now, the total generating function now S is nothing but W, that of course will be function on all these alphas. So, that would be of course alpha and there is a gamma and W Q alpha. So, W as a function of Q and alpha and minus gamma t. Okay. Now, what is this gamma? Gamma of course remember must be function of all the alpha variables. Okay. To look at it, see W, capital W function is called as a Hamilton's principal function, Hamilton's characteristic function. Now, this particular gamma here, this gamma must be function of only alpha variables, because if I put this back into the Hamiltonian, then eventually I know that the Hamiltonian is constant. Even though Q appears there, the Q somehow should cancel itself out and you must get an expression for gamma which is in terms of only alpha. Remember, only in terms of constants, not in terms of the variables Q. Okay. So, the question now we want to ask is this, and we know of course this generating function, how does it operate? It generates a canonical transformation which makes all the canonical variables constants of motion. Now, instead in this case, if I use W to generate a canonical transformation, what kind of canonical transformation it would do? As of now of course, W just appeared as, because of variable separation, W appears as just a part of capital S and capital S is a generator for some canonical transformation. What about W? W also has its own canonical transformation which also is useful in this particular case, in the case when Hamiltonian is independent of time. And remember, in the last week we had talked about two ways of doing this. One is to transform to new coordinate system where all the 2n variables become constant of motion. Another way was you transform to a new coordinate system in such a way that all the coordinates become cyclic, and in which case the solution again is trivial, even though at least all the conjugate momenta or canonical momenta will become constants of motion and the integration for q variables will be very easy. Okay. So, this is the one which I am going to look at now. So, we start with this equation, the Hamilton-Jacobi equation, where H is equal to gamma. It is a again differential equation in W. Now, the first step is to solve this and get your function W, okay, with alpha as constants of integration. Then from the Hamilton-Jacobi equation, I argued that gamma must be function of only alpha variables. Okay. So, it is some function g say. Now, we construct that canonical transformation by replacing all alphas by p. Okay. So, I get this function which is W, which is function of small q capital P. Okay. Now, see, this program is exactly similar to Hamilton-Jacobi's program, the first part of the lecture. Okay. So, the transformations which we will generate will be small p I will be equal to partial of W with small q I, and capital Q I is partial of W with respect to capital P I. Okay. Now, once you have these equations, what happens to the new Hamiltonian? New Hamiltonian, remember, which is function of capital Q and capital P. This of course, we all know already is gamma, and gamma is a function of alphas. So, alphas have been replaced by P. So, this is in fact function of only P variables. Okay. Now, you can see that capital Q will not appear in the expression of H. H is now expressed entirely in terms of capital P's. So, what does that mean? All your canonical coordinates capital Q I, they are all cyclic, they are all ignorable, and then the equations of motion is very simple. What happens to P I dot? pi dot is 0, time rate of change of p or pi is 0. That gives immediately these must be constants, okay, some constants there. And then what about capital Qi? Oh, that of course must be equal to del g by del pi, which is equal to some nu I say. Okay. And you can of course this integration of this is straightforward, and you get finally q, which is a linear function of t plus some constants. Remember, of course, nu I are already known, only constants which appear in this one are alpha I and beta I. Nu of course is known because nu comes from gamma, which is functions of alpha. So, this is in fact just the statement of the nu i's are just being calculated from alpha i's. Okay. Now, same thing, finally, I would know that capital P in terms of small q, small p and t, and I know that must be constant, and I get q I, which is also function of small q, small p and t, and that must be equal to nu I times t plus beta I. And how do I solve this system? Finally, again I have to invert this. At t is equal to 0, I can get value of alpha I. At t is equal to 0, this term will be 0 and I get value of beta I. Invert this, I get the final solution. Okay. So, this program is exactly similar to the Hamilton-Jacobi procedure. Only thing is, instead of the Hamilton's principal function, we work with Hamilton's characteristic function and use the fact that the Hamiltonian is independent of time. Okay. This is it. Let me take one example. Now, let us take an example of central forces. Okay. The Hamiltonian is straightforward, which is, so in this case I will assume that it is a planar system to begin with, because we know in case of central forces the angular momentum is constant of motion that fixes the plane of the orbit. So, I am going to assume that you have a system in which you have variables, say this is your variable r, this is variable theta, and the particles potential energy just depends on its distance from the origin. So, this is the standard setting there. Now, Hamiltonian is just p r square plus p theta square by r square divided by 2 m and plus the potential energy. Okay. Construct the Hamilton-Jacobi equation. Hamilton-Jacobi equation, remember now there are two coordinates, one is r, one is theta. So, I will replace p r by del w by del r, I will replace p theta by del w by del theta, this term here. Okay. And then you get this Hamilton-Jacobi equation. Now, I need to solve this. It is a differential equation. Think of, you probably already are familiar with differential equations of this kind. For example, to find the electromagnetic potential, you solve the Laplace equation. It is a partial differential equation and it is a potential which is function of 3 space variables. Okay. And then there are several techniques you might have already learned how to sort of integrate the differential equation. Separation of variables is one of the powerful techniques there. Okay. And we will see that we can apply that here too. So, what I will do is I will shift all the theta dependent terms to one side and all the r dependent terms to the other side. Okay. And to do that, let me first express the capital W function, which is function of two variables r and theta, as sum of two separate functions. One is function of r alone, one is function of theta alone. Then you put it back into the Hamilton-Jacobi equation there and do the rearrangement. If I do the rearrangement, I can put all the theta dependent terms on one side. Remember, W2 is a function of theta alone. So, on this side I have only theta dependent terms. On this side, I have only r dependent terms. Okay. Same argument. Remember, without this part, I will initially say that this is not there. This is just the rearrangement of the Hamilton-Jacobi equation. This must be true. This is a point equation. So, it is true at all r and all theta. Okay. And now, this can happen only if at all r theta, this must have exactly the same value. Okay. It must be constant. The equation, I will set it equal to some constant there. Okay. So, now you have actually using separation of variables separated that one differential equation into two separate differential equations, one in r and one in theta. Okay. This part of the differential equation is very easy to solve. So, W2 is in fact simply equal to alpha theta. So, I am of course going to choose the factor there as minus alpha theta square, because I already know the answers. I can preempt the ease of the calculation. So, in this case W2 will just turn out to be alpha theta into theta plus constant. Can you see that I can do that integration very easily? The second integration for W1, that is slightly harder, but not difficult. So, if I again rearrange all the terms, I can take this r square to the right hand side. So, it will become alpha theta square minus r square, and then you can take this 2m times gamma minus v also to the right hand side and take a square root. So, you get this, and then of course, the answer would simply become W1 will be integral of this function. Okay. So, from here I can write down the final W function, which is sum of W1 and W2, and W1 is nothing but integral of this quantity, which is 2m times gamma minus v minus alpha theta square by r square. Of course, we recognize the alpha theta square. Alpha theta square is nothing but the angular momentum square, okay, and plus alpha theta into theta. Okay. Now, we are going to put gamma. So, to choose, now we have got this W in terms of r theta and alpha r and alpha theta. Okay. 4 constants there. And what I am going to do is, of course, I do not have alpha r which is immediately visible here, but instead I have this constant gamma there. Okay. So, I have W which is function of r theta, gamma and alpha theta. So, I will choose my new coordinates, new canonical momenta, put P r, P gamma as gamma and alpha theta as capital P theta, and then your capital Q r, okay, will be equal to del W by del P r, but that is exactly equal to del W by del gamma, and then because remember we have put that P r to gamma. So, then look, where does the gamma appear? Gamma appears only in this part. So, this would appear only here, and remember, because the Hamiltonian is the variable q, capital Q is now cyclic, I already know that its integration is t plus beta kind of thing. Okay. So, finally, I get for q r the expression like this, and you remember this expression is very common. We have done central forces in our BSc, and when we did that, we have come across this particular equation, and similarly theta equation also can be gotten here. Theta equation, can you see that will appear only in r and theta. So, in fact, the second equation here, which is for q theta, that will give you the equation of the orbit directly into r in terms of theta or theta in terms of r. The first one will give you the time dependence. Look, in the second equation, the time dependence is completely missing. So, this is the expression of r, implicit expression in r and theta. So, this in fact will give you Keplerian orbit if your central force was just 1 over r kind, and the speed with which it moves along that trajectory is of course coming from this first equation here. All right. So, this was the method using Hamilton's characteristic function, and this of course applies only to the Hamiltonian which are independent of time, that means they are also constants of motion. Now, there is another specialization which we can do of the same procedure, which of course enormously helps in specific kind of problems. The kind of problems are the periodic problems, and these problems of course appear many times in our natural systems. The periodic systems, I can classify these into two kinds of motions. Okay. One motion is when you plot it in phase space, this would look like a closed orbit. I will give you an example. In case of harmonic oscillator, what you get is the harmonic oscillator potential, and if you mark the energy, then you get two turning points, okay? One at plus amplitude and one at minus amplitude, and then there is a turning at these 2 points, and the system keeps doing oscillatory motion between the two. And remember, in the examples of phase space, we already had looked at the harmonic oscillator. What kind of trajectories we get? We get those ellipses. Okay? In general, in a motion of that kind, you have two turning points. Here I have marked them as q prime and q double prime here. So, what happens at turning point? The kinetic energy becomes 0, or outside these bounds the kinetic energy would be 0, and the motion is turned back, the trajectory is turned back towards the center there. Okay. And similarly for the turning point at the other side. Now, of course, these will not be always harmonic motions. You take for example, central force problem, just a Keplerian problem. In the Keplerian problem, if you look at the R equation, then you have effective potential, and in the effective potential, so if you remember this diagram, you have effective potential here, and if you have energy E, then I get two turning points, one turning point here, one turning point here. So, in the R variable, there is a turning at some R1 and R2. Okay. So, if you look at PR-R plane of the central force problem, then you have trajectories of this kind. The typical motion here is oscillatory, and that is why this also is classified as oscillatory. Think of also another possibility of simple pendulum, where the pendulum just goes back and forth between plus theta and minus theta. The other kind of motion where the periodicity happens is in fact when you have a geometry of a phase space which is compact in nature. By compact, I mean if the variable, the canonical coordinate, is like an angle which repeats itself after 2 pi, then remember when I was talking about the geometries of the configuration space, you get a compact geometry. That means along theta direction, the geometry is like a closed circle. Now, what will happen in this case? In this case, if the variable or canonical coordinate in this case, which is angle, which goes over 2 pi, then of course you would have situation like this. So, you have some angle here and then add another 2 pi to it, you get another, and then at that point, if the momentum value is same, then this momentum graph or the trajectory that you see in this section is again repeated in the next section. Okay. So, there is a periodicity in q. So, if I add for example to q variable another q naught, then I get invariance or a symmetry, and that causes this kind of periodicity. And typically these must be the angle variable kind, and these are the ones where the motion will continue through the across the compact region there. Okay. Here are the examples of this. The both kind of trajectories can happen in the same system, and in fact, you do not have to go too far. This is a very simple solution to simple example to this. Take a simple pendulum. Simple pendulum, suppose this is the, so I will draw the simple pendulum here. Oh, I have already here. So, if this is the angle theta, which is what is plotted here. So, this is the angle theta and this is corresponding momentum p theta. Okay. Now, look at the kind of trajectories you will get. First of all, from the bottom, if you give the simple pendulum certain amount of energy which is less than 2 times mgr. 2 times mgr is the, so if the radius is capital R, 2 times mgr is the energy that is needed for it to go to the top point. Okay. And if you give energy more than that, it will of course swing across the top point, but if you give energy less than that, then you get this kind of motion where you have oscillations. Okay. So, the oscillations happen between two angles and there are turning points there. So, essentially turning point means the momentum must become 0, that is characteristic of this. It is not only closed orbit, but there is a turning point, that means it passes through the theta axis, the trajectory passes through the theta axis. So, these trajectories which are shown here in blue, these are all oscillation kind. Now, if you give sufficiently large energy more than 2 mgr, then it will swing by and it will complete a rotation and then it will go on rotating, and the kind of trajectory you would get. So, for example, if I mark this point and this point, and you can see that now if you go beyond this point on theta axis, the trajectory keeps on repeating. Okay. This is the nature of the rotation kind of trajectories. And now, what are we interested in? In most cases, the kind of answer that we want is usually, instead of the detailed motion of this periodic motion, what we want is probably just the frequency, and this is of course a crucial question in most problems, and there is a shortcut method to do that, and this is called as the action angle variables. So, let me write down the procedure first. Let us start by, I will first apply it only to a system with 1 degree of freedom. Okay. Once we understand this, then the extension would be straightforward. Of course, this does not easily apply to extended systems, but what are called as separable systems. You remember in the previous example of the Kepler problem, of the central force problem, I said that we could separate r variable and theta variable. If I have system with n degrees of freedom, and if I can separate the Hamilton-Jacobi equation into separate equations, one for each variable, then I say it is a completely separable systems. And this action angle variables method, this of course will extend for such systems very easily, but that is later. Start with the Hamiltonian with 1 degree of freedom, and I will assume that Hamiltonian is independent of time t. Then of course, h can be written as, or h is a constant of motion, and I can set it equal to some constant alpha. Now, you see this is just the equation in p q, and that is equal to alpha. Can I invert this? Yes. So, in fact, I can write p as a function of q and alpha. Okay. Now, I am going to define, remember we are talking about the periodic motion here. So, I am going to define a variable j, and which we will call it as action variable, and define it as integral of p dq. I can do this, remember, because I already know p in terms of q and alpha. Okay, alpha is just one constant. So, this variable j, remember that integration with that circle there means over one cycle, okay, one cycle or one period of the periodic motion, and call that as variable j. Now, once you integrate this, remember p is function of q and alpha. Once you integrate over q, what is j function of? J is function of alpha alone, and then I can invert this relationship and write alpha as a function of j. So, j would be function of alpha alone, and then you invert this and write alpha as a function of j. But then what would that be? And that would simply be Hamiltonian written in terms of j. So, what we have managed to do is we have managed to find one variable in such a way that the new Hamiltonian now is function of j only. Okay. Now, let us get back to the standard procedure. So, find now w which is function of q and capital J. Remember, this is exactly the same procedure, because it is one degree of freedom. I had one constant, that was alpha. I am going to replace alpha by capital J, the action variable, and call it as new momentum. Okay. Once you call it as new momentum, now I have this generator of the transformation or Hamilton's characteristic function, which is written in terms of q, which is the old coordinate, and capital J, which is a new momentum. Okay. And we of course find that by solving Hamilton-Jacobi equation for this case. Now, small p is nothing but del w by del q, and new variable, okay, new variable I am going to call it as variable w is del w or partial of w with respect to new momentum, which is capital J. Okay. So, now equations of motion are straightforward, because the Hamiltonian is function of only j, that is the new momentum. The corresponding new coordinate w is cyclic, and hence j is a constant of motion. So, j is constant, and what would be w dot? W dot is nothing but partial of h with respect to new momentum j, and that is equal to some constant nu. Okay. And then we can integrate this, w would be equal to nu t plus beta. Okay. So, this is straightforward there. In fact, this is the reason why it is called as angle variable. Okay. Now, what can we do with this? As of now, I have not done anything new apart from the Hamilton-Jacobi procedure. I have just managed to find new coordinate and new momentum such that the new coordinate is cyclic, which is what we did earlier too. But the advantage of this is in fact seen if you look at the w variable more carefully. Now, what I will do is look at what happens to w variable over one full cycle. If over one full cycle, I can calculate the change in w as del w by del q into dq and integrate this over one period, okay, or one cycle. Now, we already know w is nothing but partial of capital W divided by partial j. Put it there. Remember, j is a constant of motion. So, I can interchange this order of the differentiation and also order of the integration and differentiation except for q, and then write this as partial of the entire expression with respect to j, and then expression would be integral of del w by del q into dq. But what is del w by del q? that is nothing but small p, the old momentum, and then this in fact comes to integral of p dq by what was this? This is nothing but the variable j. So, partial derivative of j with respect to j, that is 1. Okay. This is the key thing in the entire calculation there. Now, if I denote the period, time period of one cycle by tau, then very simply change in omega is nothing but, remember that nu times tau. Okay. Remember the equation for W is nu t plus some constant beta, but nu, so beta of course will go away when you take the change in W, and this would be nu times t, and then you get tau, which is 1 over nu. Now, you see why I had used this symbol nu. Nu is a favorite symbol for physicists or of physicists for frequencies. In fact, if tau is time period, clearly nu is the frequency. And how did I get the frequency? It's just partial derivative of h with respect to j. So, you see I actually do not have to do all these calculations which I did in between. I start with the Hamiltonian, calculate the action variable. Once I calculate action variable, I need to figure out how Hamiltonian depends on the action variable. Once you do that, you get the frequencies. Okay. So, a shortcut to get frequencies of a periodic system. Again an example. So, I will take the harmonic oscillator as an example. Your Hamiltonian is p square by 2m plus half m omega square q square, and I will set it equal to alpha. Okay. Now, express p in terms of alpha and q, that is going to be just 2m alpha minus m square omega square q square to the power half. This is just obtained by inverting this relationship or rearranging this expression there, and then calculate j. Remember, j is to be integrated, or to calculate j I must integrate that p over one cycle, remember that. So, I will put that p there. So, that would be square root 2 m alpha by taking square root 2 m alpha common out of this, and what you are left with is integral of 1 minus m omega square by 2 alpha into q square to the power half. This is a easy enough integral, okay, and we do not need to do much for integrating this. So, the obvious change of variable is to put it to some theta. So, I will substitute q as 2 alpha by m omega square to the power half into sin theta. Now, the integration is straightforward. This will become sin square theta, 1 minus sin square theta will become cos theta, and what would be your dq? dq will be equal to the constant multiplied by cos theta d theta. So, essentially what you get is j will be equal to that constant which was earlier there. The integrand will simply become cos square theta d theta multiplied by this constant which comes from the substitution, and that is exactly equal to 2 pi alpha by omega. Remember, we are supposed to do this over one cycle. So, that means this in fact can be replaced by integration from 0 to 2 pi, and then the integral is straightforward. And now, what is your j? So, alpha, remember, represents your Hamiltonian. So, alpha is Hamiltonian expressed as a function of j, and that is exactly equal to omega j by 2 pi there. And we know that whatever, I still have not calculated the generating function or Hamilton's characteristic function yet. I have not calculated the second or new canonical canonical coordinate yet, but I already know the frequency of this system because it is in oscillatory motion just by calculating this. Once I calculate this, what is the frequency? frequency is nothing but partial of h with respect to j, and take that partial of h with respect to j is just omega by 2 pi, and that is the frequency of your harmonic oscillator. We already knew that, but it is nice to do this exercise, because for other systems I am going to find similarly the frequencies which are not so obvious. I can apply this to even Keplerian problem, which I will do in my next lecture. So, I will of course complete this problem and calculate the other parts of the puzzle. I will not just leave it at the frequency. So, now the del W by del Q, this must be equal to P. Remember, W is the generator of canonical transformation. So, partial of this with respect to Q is P, and P we already have rearranged this to get this. Okay. So, now I can calculate W function very easily, and the one constant of integration is already there. The second constant of integration is additive in nature, we will not worry about it. So, integrate this. When I integrate this, remember, unlike j, the j variable, the action variable was integrated over one period. What should I do here? No, I am not going to integrate it over, it is not a definite integral, it is an indefinite integral. So, there are no limits. I must get a complete solution to this, including the constant of integration. If I do definite integral, I do not get that constant of integration, but in this case I need to get one. Okay. So, integrate this, the same substitution will work. Okay. So, Q can be substituted by some constant here multiplied by sin theta. Put it back into the equation and integrate for W. So, then it is a exactly same integral, only thing is it is in the indefinite form. So, this one also will boil down to integral of cos square theta d theta. Express your cos square theta as 1 plus cos of 2 theta by 2 and integrate 2 pieces, and then the cos of 2 theta will integrate to sin 2 theta. You express it again back in terms of sin theta and cos theta there. So, your W variable is this Hamilton's characteristic function now can be expressed as j by W j by omega. This is a possible confusion there. I have same symbol omega which looks like W, but this is not the coordinate, sorry. This is j by omega. Omega was a constant in the Hamiltonian, is theta plus cos theta into sin theta. And now, once I have this W, now I can calculate the new canonical coordinate. What is the new canonical momentum? That is capital J already. Okay. Now, calculate this. I am going to leave this calculation to you people. Take a derivative of W with respect to J. Remember, J appears here as a multiplication, but J is also there in theta. Remember, Q is this after substitution. When we went from Q variable to theta variable, there is alpha there. Okay. Remember, I must substitute this alpha by J. When I constructed W function, I replace all alphas by the new momenta. So, new J will appear here. So, your theta includes J. So, when I take a derivative of capital W function, Hamilton's characteristic function with respect to J, oh, there are going to be lots of terms there, and all those terms will cancel to leave you, or simplify to leave you with one very simple answer, that is theta. Not unexpected, we already knew this. So, your theta variable is the new variable which I wrote as W in the earlier one, and what is the form of this? This is nothing but omega t plus beta. Remember, the frequency times t plus b. Okay. And then the solution looks straightforward. Now, the Q is nothing but some constants into sine of omega t plus beta, and this is a very powerful method to calculate the properties or the solutions of periodic systems. In the next class, I will talk about, or I will use the same action angle variable method and apply it to the Keplerian problem.